So welcome to the day 5 of our coding session, right? So which is a complementary class for the lecture for day 5. All right, so we're going to be practically explaining and implementing the day 5 lecture where we started introducing XGBoost. All right, so in this coding session, we're going to introduce and provide a comprehensive explanation on how to build, evaluate, and visualize an XGBoost regression model using the household power consumption features. All right, so you're going to have an interesting time as we go through this coding session. All right, so we have moved from the simplest model, which is the linear regression, into a moderately advanced model, which is a random forest, which is also a regression model. And now we are moving to a more advanced machine learning model, which is known as the XGBoost. Right, so the first thing we need to do, if you haven't installed XGBoost, you can kindly do that by typing this line of code, pip !pip install XGBoost. Okay, and then you can introduce this hyphen quiet. So this means it's going to install without having to show you all of those processes and all of those logs, right? So make sure you install the XGBoost or XGBoost model into your working environment, into the environment you have created directly on either Anaconda. So whichever method you have used, please ensure that this is installed directly to your environment. So my Jupyter notebook has been initialized from my environment, so I can do this and it will install directly to my environment. Nevertheless, I've already installed XGBoost. So all I just need to do is to import it. All right, so I'm going to comment this line because I've done this already. For those of you who haven't done it, please ensure you start with this. Now, the next thing we need to do is to import the libraries that we need, including the XGBoost. So the first thing we need to do is to import these important libraries, or I'll say import Pandas as PD, import NumPy as NP. All right, so we need to import Matplotlib dot pyplot as PLT. Right, so we need to also import the almighty XGBoost model. So we say import XGBoost as XGB. Okay, the boost should be spelled with double O. So once we do this, now let me take you through a brief description of each of this model. Remember, Pandas, we use Pandas for loading our data and also handling tabular data. And then we use the NumPy library to carry out numerical computation. We use the matplotlib.pyplot library to plot and visualize our model, the graphs, to see the training behavior and the pattern of the graph. While the XGBoost is nothing but the gradient boosting algorithm for a supervised learning. All right, so this is a supervised machine learning model. We use it for supervised learning on a regression task. All right, so the next thing we need to do, we run the cell. Upon running this cell, we don't have any error. We need to go straight to data loading. So we need to load data. All right, so for we to load our data, we need to say df, which is nothing but a variable. We want to store this data into pd.read underscore CSV, and then we introduce that. We say features dot CSV. So this is the name of our data set. But before we run this, we need to ensure that this data set is exactly where we're working from, else it's going to throw a kind of error. But if we don't have it, all I need to do is to copy the path. So this is where I have the data set. This is the data set called features. All I need to do, copy the path to the folder. All right, so I clicked on top of the directory path, okay, to the folder. I copied, and then I went back to my Jupyter notebook, and all I just need to do is to paste that within this path and then introduce the backward slash, and then I introduce the raw string, which is R, which is going to invert all of this backward slash to forward slash, and then recognize where the data is or the data set, and then it's going to load it into the variable called df. Right, so the next thing we need to do, just like we have done previously in our previous class in the day 4 coding session, all we need to do now is to read the data containing the features and also prepare the target values for the energy forecasting. So all we need to do, so the X column or the X will contain input features, okay, which is going to exclude the target and the timestamp, and then the Y will be the target variable, which will contain the global active power. Okay, so that's what we want to predict. So exactly what we did in the previous coding class, we're going to have Y equal to. All right, so for those of you who went through the previous class, you're going to notice that this is repetition. So we're going to say, we're going to drop, most importantly, the columns. Okay, yes, before we do that, I usually like to display the columns that we have. So we say df dot columns. I think this is a good practice. Okay, so we see all of these columns. So the next thing we need to do, we need to start dropping these columns. All right, so we say not all. Okay, so we're not going to be dropping all, we're just going to be dropping what we don't want as part of the features. Right, so in this case, this is going to be a square bracket indicating that this is a data frame, and then we're also going to drop the timestamp. Where is the timestamp? Okay, we have the timestamp. Then we introduce the square bracket, and then we close the parentheses. All right, so y is going to be y equals to data frame, because this is a data frame, and then we're going to introduce the square bracket, and then we're going to assign the target variable to be the global active power, which is what we want to predict. Okay, so once we have this and run this, we shouldn't have any error, but if we do, we're going to fix it, don't worry. It says x, okay, so it has to be equal to, all right, so that's it. All right, it's fixed. So the next thing we need to do is to split the data set using the same method. All right, so now we have been able to prepare data and separate them into the features and the target. The next thing we need to do is to split. Okay, so we say x underscore train, comma, x underscore test, comma, we say y underscore train, comma, we say y underscore test equal to, so we have to import the library. Okay, so in this case, we need to introduce the test, no, the train, we call it the train underscore test underscore split, okay, which is, okay, this is a typo. So which split, which is a method, okay. So, but before we can achieve this, we need to import this. So it's going to be from Scikit-learn dot model underscore selection import train underscore test underscore split. All right, so and then we need to introduce the X, which is the features. We need to introduce the Y, which is the target. We need to also set the test size. All right, test size should be equal to 0.2. Also, automatically it's going to assign 20% to the test set and then the remaining 80% to the training set. And then we need to set shuffle. Okay, shuffle equal to false because this is the time series data and we want to avoid data leakage. Okay, so we need to do so. Let's run this code. If we have any error, we're going to sort it. Okay. Okay, it says we have an error. It says from invalid syntax we have. All right, it says this is supposed to be underscore. All right, so I think I've been struggling with that. Okay, underscore and hyphen. Sometimes I do make the errors. All right, so it means everything went on well. Okay, so we have settled this. So we'll split the data into 80% trading, 20% testing. That's what we have done. All right, so we have shuffled, we have set shuffled to equal false. Like I said, in order to preserve the temporal order for time series consistency, where we have the older part of the data in the training subset, and then we have the newer part of the data in the test subset, so that we can use the historical data to predict the future demand of energy. All right, so this will help us prevent data leakage. So the next thing we need to do in XGBoost, you cannot train the model XGBoost directly using the data that we have splitted into train and test. We need to transform this data. All right, so we need to convert this data into XGBoost optimized internal data structure. All right, so which is faster and more efficient for training. So all we need to do is to use or create the D matrix. Okay, so we're going to use the D matrix function to be able to convert this data into the XGBoost compatible structure. So what we need to do is to say dtrain equal to, and then we have dtest equal to. So we're going to do for both train and test. So we say XGBoost. So this is an inbuilt function. We say D matrix. Okay. So this is to help the computation. Okay, we say X underscore train. All right, so we say comma label it should be equals to Y underscore underscore train. All right, so we're going to do this for tests as well. So it's going to be X test and then Y test. All right. So successfully, if we run this cell, if there's any error, we're going to fix it. Okay, there are no errors. So successfully, we've converted that to the optimized internal data structure of XGBoost. Okay, so you do this for XGBoost. You cannot skip this part. You cannot skip it. All right, so take note. XGBoost is a more advanced machine learning model. All right, so the next thing we need to do is to set the XGBoost parameters for training. All right, so this is where you have control over the parameters, which controls the performance of the model. So these are parameters that you can tweak, you can optimize in order for you to get a better result. So we have the params, okay, equal to, we have the curly bracket, which is more like a dictionary, and then you have the curly bracket. All right, so the first parameter is going to be quote objective. So what is the objective of a machine learning model? The objective of a machine learning model is to reduce the residual error or we say the differences between the actual and the predicted. So the most important or the objective is to see how well can the loss be minimized. So in this case, the objective is going to take a regression loss, which is going to use the square error loss. All right, so we're going to set it, we're going to say reg colon squared error. So we're going to put the quote and introduce the comma. Okay, so the next parameter is the max underscore depth. So what maximum depth do we want to set? Okay, so we're going to set that to 6. All right, and then what that means is this. It means the maximum tree depth. This controls the model complexity. So the more the value, if you increase the value to 100, so it means you're making the model more complex. Although increasing the value also increases the performance as well. But it gets to a certain point where it could lead to model complexity and then gradient vanishing problem. Okay, at this point, the model begins to perform poorly. All right, it could lead to overfitting. And then if the value is too small, it could lead to underfitting, and sometimes it could also reduce the performance of the model. So the best value is determined by you based on your ablation study and hyperparameters optimization. So you have to have this in mind. So the next parameter is the learning rate. So we use this to say ETA as the abbreviation for learning rate. Okay, we set the learning rate to be 0.1, which is a little bit large. Okay, we could take it as low as 0.001. All right, so the learning rate controls the learning process of the model. It's nothing but the step size that determines how the model should learn. Should it learn very fast, slow, or moderately? Now, if the learning value is too fast, there's an issue that can lead to overfitting. That's if it's too large, it could lead to overfitting, whereby the step size can be very big and it could be jumping from one point to another and never get to the global minimal. And then if it's too slow, it could take a long time to converge. Just the right size or the right value is perfect. So how do you get the right value? You have to interpolate, you have to experiment to get the right value. All right. So the next hyperparameter would be the sample, the subsample. Okay, we have code, we have subsample. So we have to set that to 0.8. Now 0.8 is a good value because if the value gets too high, maybe 0.9 or 1, it could lead to overfitting, because what this means is the proportion of training samples used per boosting round. It means for each boosting round, for each airport, for each training time, we want to supply 80% of the training set to each of the trees. All right, so this is what happens. So randomly, it's going to take 80% of the training set and supply to each of the trees during the training. So the boosting round during the training rounds. So that's what happened. So if you set any value less than 0.5, it could also lead to underfitting because the model is not going to be learning that much. But if it's something too high, 0.9 to 100, it might lead to overfitting. The model will start learning noise. So 0.8, which is 8%, it's quite better and good. So now we have the next hyperparameter is we have the column. Okay, we say call sample. We have the column sample underscore by tree. All right, so what this means is this: we need to assign a range to say 80, okay, also 0.8. All right, so this means that okay, All right, so this means the fraction of features used per tree, meaning that if you have like 10 features, it means 80% of these features should be assigned to each of the tree during the boosting round. So this allows for randomness and also allows for more training, and then each of the tree is going to learn from the error of the previous tree. So every tree, as it comes down, every new tree is going to learn from the error, the previous error from the previous tree, and then use it to improve during the next round or boosting round. All right, so that's how it goes. And then we have the final hyperparameters we need to set, and then we have the seed, right? So we have seed. Okay, let's put this in quote. We say seed column. So we set seed to 42. So this is a universal constant that has been used by a different machine learning expert. So the random seed is used for reproducibility, that allows us to reproduce the same result each time we run the code. All right, so these are the major hyperparameters. So if we run this cell, we shouldn't have any issues. If we do, it's okay, we're going to fix it. All right, so in this case, it says ETA. We need to have a comma. So it's pointing to ETA, which is behind. So it means at this point, we're supposed to introduce a comma, not a full stop. And then if we run that cell, we'll notice that everything becomes perfect. So the next thing we need to do, we need to train the SG model. So before we train, we need to introduce the numbers of rounds, which is the number of boosting round, which is the training time, or sometimes we can call it the epoch. If you're into deep learning, all right, so we can call that the epoch as well. So the number of boosting round, so round number underscore round, okay, will equal to, so let's set that to 100. Okay, so that makes sense to some extent. And then we need to also set the, we want to see the evaluation result. We want to see the training result during each round. So we can store that in a kind of dictionary as an history, training history. So that is what is popularly called training history. So we say evaluation equal to, or we call it evaluation underscore result. Okay, so we understand that equal to, so we call this a kind of dictionary. All right, so the next thing we need to do is to train the model. Okay, so once we have all of this, so we say model equal to, so we say xbb dot train. All right, so in the previous model, like the linear regression model and random forest model, we use dot fit, which also means to train. In most deep learning models, in fact, all deep learning models, we use dot fit, okay, and then which is similar to regression and random forest. But for XGBoost, we use dot train. All right, so we need to introduce we need to pass the parameters, say, or the arguments. We say params, which we have defined, and then we need to train using the data. We need to fit the model into the data. So we say which of the data, training data, is going to be train. All right. And then we need to also mention the numbers of rounds. So we can say number underscore boost round underscore round is equals to the number underscore round. Okay, so let's introduce number of rounds. Let's introduce that as number of rounds. Okay. So what other argument we need to supply? We need to also supply, now we want to save all these evaluation results. So we say evaluation will be equal to, we're going to introduce a list, and that list will have the train, right, comma, quote, train, okay, and then we're going to have a close parenthesis, And then we're also going to do for the test, we're going to open another parenthesis, we say the test, okay, comma, we're going to have test as a string, comma, this is going to display that as a name, and then we have curly bracket, the square bracket close, and then we pass another argument, which will be the evaluation underscore result that we have defined set. Okay, it's going to be evals underscore result. Okay, so that will also give us evaluation result. Okay, so equal to comma, we have the verbose. Okay, so we have the verbose equals to let's say 10. Okay, now we say verbose equals to 10. What does that mean? It means it should display the training process. It should display at every 10 rounds. So when we set verbose equals to 10, it's going to display the result. It's going to display the training result. Okay, we say verbose underscore, okay, evaluation rather. So it's going to display that after every 10 rounds. And then let's see if we run this code, if we have any error, we have to fix it. Okay, so it's going smoothly without any error. So the next thing we need to do is to save our model. Okay, we need to save the model. All right, by saving the model, all we need to do is to say model.save, which is straightforward, underscore model. And then we need to introduce what is the name of the model we want to save it with. So we say xgboost, okay, underscore day5. Okay, so we're going to say day5 underscore model. Okay, so we're going to save this with a format called JSON, which is the recommended format when saving the SGP model. All right, so once we do this and run, so we could say the result, okay, we could say that the result makes sense, okay, both for training and test. The next thing we need to do is to predict on the test data. So let's predict this model, what we've done. So let's predict on the test data. All right, so all we need to do is to say y predict, okay, y pred equals to the model we have trained, which is this model we have trained. This is the same way you do all machine learning model. Okay, the model you have trained, you say dot predict. Okay, so we're going to predict using the test data, so which is the D test from the D matrix. All right, so once you do this, simply one line of code, okay, it means the prediction is saved in this variable called y predict. The next thing that we need to evaluate the performance using the RMSE loss function. All right, so the next thing we need to do is to evaluate. So let's write the evaluation. All right, so the next thing we need to do is to say RMSE equal to. All right, so we need to remember this formula. All right, so we need to understand that it's the square root. So RMS is nothing but the square root. So we're going to say NumPy dot the square root. So this is square root, right, of the MSE. So MSE, we imported the MSE. Did we import the MSE loss? Okay, if we did not, so we're going to do that from this part. So we're going to say from scikit-learn dot metrics. Okay, remember that metrics import. What are we importing? We're importing mean underscore squared underscore error. So that's what we're importing. Okay. So we have that as the mean square error. So this is what we're importing as a method from Scikit-learn. So it's a method. It comes with a parenthesis this way because it's a method. So we need to supply an argument. So the argument we need to supply is the y test and y predict because it's labels. So we're going to say the label. Let's see if we're going to get the right prediction, and then we have the y predict. All right. So once we do this, and then the next thing we need to do, we need to print the result. So let's see if we print the result, what we're going to get at the end of the day. So let's say print arrow MSA. I'm supposed to have another bracket here. Okay, good. So if we have to print that result, print RMSA. So let's see what we're going to get. So if we have any error, we're going to deal with that quickly. All right, so we have our result printed 0.009. Wow, that's quite low. So like I said, printing result this way doesn't look nice. All we need to do is to introduce the F string, all right, which allows us to print our result arrow MSE colon, and then we introduce a curly bracket. I'll put this into, okay, oh no, curly bracket, and if we run this, we should be able to get an error. Okay, the error is coming from the fact that we did not introduce the code. All right, so now we have the result RMSA, but then this result is too large. How do we introduce like 3 decimal places? All right, so let's make it look nice. Yeah, let's make it look nice. So all we need to do, okay, so we need to introduce that within the curly bracket dot 3 decimal places, and then let's see. All right, so we have 0.10. Okay, so that looks nice. So the next thing we need to do is to visualize the learning curve, and then thereafter we can see if we can plot the future importance. So let's visualize the learning curve. Okay, so let's say we have PLT dot figure. All right. Please don't get tired in writing the code, and then we have this as a method for Matplotlib. Okay, so if I have to run the cell, let me see. All right, it's working very well with the default size. All right, so I want my own size, fig size equal to, so what will be my figure size? Let's say 10,5. I think I like using this. All right, so if I have to run this, it's going to change that to, okay, that is the inches, okay, 1000 by 500. All right, so I've gotten this correctly. So the next thing I need to do is, let's see how to plot using the training history. All right, so the next thing we need to do, we say PLT, so that works. PLT.plot. So let's plot the this. We already saved, the result has been saved in this dictionary. So let's take it from this dictionary. The result has been saved there. So that's what we want to plot. We want to show the result there. I'm going to say evaluation result, and then we're going to put this into a list, and then we need to specify what we want to plot. Okay, we want to get the name as train, So once we get that name, so Python is going to display that name train, and then also is going to present for us loss, which we have here. Right? And then the label, we want to have a label. Okay, so it's going to give us label will be equal to train RMSE. So have it as train RMSE. Right, so in this case, we have, okay, we have our plot. So we're going to do this for both train and test. All right. So all we need to do is to change this to test. Then we also need to change this one to test, so it's the same. All right, so having done that, the next thing we need to do is to supply title. Okay. So let's run if we're going to have any error. Okay, no error. Good. So we have it there. Okay. We have the train and test. All right, so let's see what the title should look like. plt.title. Okay, so what should be the title of this graph? So we're going to call it XGBoost learning curve. So say XGBoost. XGBoost is not spelled well. Okay. Learning curve. All right, so we need to specify the labels, the x-axis and the y-axis. So on the x-axis, we're going to have the boosting rounds, which is like similar to the epoch. All right, the training time will be on x. All right, so we're going to have that as plt.x label. All right, so we're going to have this as the boosting round. So call it boosting rounds. And then the y-axis plt.y label for the y-axis. So we're going to call this the loss. Of course, it's going to be the ROMSE loss. And so next thing we need to do, we need to set the legend. Okay, so let's run this and see how it looks like. All right, so we have the loss and the boosting round. Wow. The loss, the curve converges smoothly. Right, so let's introduce the legend. So we're going to say plt.legend. Okay, so which is a method in Matplotlib. Once we do that, it's going to introduce for us a wonderful legend because we have described the label. So the label we described initially, which is the train RMSE and the train and the test RMSE automatically takes that as the legend. Right, so the next thing we need to do after setting the legend, we need to, okay, so let's introduce a grid. Okay, so let's introduce a grid to the plot. So plt.grid. All right, so that will determine, so since it's a method, so we need to say true. So in this case, we say true. What happens? Introduce for us some green lines. Okay. So in this case, our graph is looking so nice. And then finally, it's a good practice. We want to get rid of information that are not necessary. Just only the plot to say plt.show. So this is going to give us a clean plot. Okay. Now we could see that the model performs very well. The loss reduces. It starts from a very high loss, and during the boosting round, we could see how the loss decreases smoothly, exponentially, gradually, and converges. This is a very good model. The dataset has been well prepared, well engineered, and well processed. So now let's see the features. Let's see the feature importance. So we're going to say XGB or SGB, okay, dot plot underscore importance. Okay, so this is an inbuilt function from SGBoost. We're going to say model, comma, max number of features. So what is the max number underscore features equals to 10? Okay, right, so this is a straight line code, and then all we need to do is to say plt dot title, just like we've been doing all this while. Okay, so what is the title? We want to call it, we call it top 10 features. Okay, importance. Okay, we'll call it feature importance. Then I'll put a quote and close the parentheses. And then finally, what do? We say plt.show. Okay, so let's run this without the plt.show. Okay, so let's get rid of all this information we don't need, that text and all of that. All this information we don't need them. Let's take them out. So once we introduce plt.show, okay, so this is going to clean up all those and just present the graph to us only. Okay, so we have this. Okay, so these are the top 10 features that contribute to the prediction. So the number one feature that contributes to the prediction is the apparent power. So we are predicting the global active power, and then the important features that helps in the predicting process is the active power, the apparent power, because the apparent power is nothing but the combination of the global active power and the global reactive power. So in this case, our model has been able to show us to visually provide an insight as to how the model came to its decision making, okay, by focusing more on the apparent power as the most influential and contributing features. So in a summary, we've learned how to load and prepare datasets. We've learned how to initialize and tune an SGB boost regressor. Maybe you're wondering how to do that. Is just to change the values. For example, let's have a maximum depth of 10. Okay. So let's make the learning rate a little bit lower, 0.01. Okay, let's increase the numbers of rounds, which is the training time, the numbers of training time from 100 to 200. So this is how to tune your regressor. All right, so what else can we tune? So those are basically what we can tune. All right, so in this case, we can run our data set from this point. Okay, so we can begin from this point. So let's see what result we're going to get. So you can fine tune to get a better result. But then our model is already producing a very good result, but we can tune to see what the result will look like from 100 numbers of rounds to 200. So let's see, in that case, you have learned how to fine tune your SGB regressor. So, and also we have learned how to evaluate the model using the train test split. Okay, so we can see how it looks like. Although now in this case, we have seen that the global reactive power becomes the top 10, the top influencing features. In this case, the model is not performing very well. We could see the loss is not as low as the previous model. All right, we could see how the loss started and the convergence is very slow, very slow. It took a long time before it could converge. In fact, it's not converging because both lines are not very close. So in this case, increase in the numbers of rounds and increase in the depth has made the model more complex and the model is overfitting. All right, so 10 for the maximum depth, it's not a good value. So 6 remains the good value, and 200 as the number of rounds is not a good value. So therefore 100, it's a better value. So in this case, we could see how increase in number might not directly relate or directly increase performance. Okay, it doesn't mean when you increase the values and you automatically increase the performance. Sometimes it could even lead you to a more serious problem. So you need to be very careful when tuning your hyperparameters for increased performance. And then we've been able to see and learn how to visualize our model performance and also features importance. So let's see what the result looks like. All right, so our model is not performing very well anymore, but then it returns back to our apparent power, which is the top influencing features. So these are the things you're going to come across, you're going to experience when training your model, when tuning your hyperparameters. Okay, so if you've gotten to this part of this lecture, it means you have learned something very significant and impactful. All right, so see you in our next video, which is going to be the day 6. All right, then. See you, we meet. Goodbye.